All right, so we're going to be looking at quadrilaterals and properties of parallelograms, okay? So I wrote out the notes ahead of time if you guys want to write it along and listen to the explanation and draw the figures, but I'm trying to shorten up the video since there's just a lot of definitions and theorems here, okay? But the first definition we're going to look at here is a quadrilateral, and it says it's a closed geometric figure with 4 sides and 4 vertices, okay? Well, that makes sense because quad, meaning 4, lateral, meaning sides, 4 sides, okay? So it could look something along the lines of maybe like this guy here, okay? Notice there are 4 sides and we also have 4 vertices. It could be something along the lines of this guy, okay? Where you have 4 sides, 4 vertices, okay? Or maybe something a little bit more abstract, perhaps. More like this guy, okay, where it also has 4 sides and 4 vertices, okay, 1, 2, 3, 4. So that's a quadrilateral. Now, a specific type of quadrilateral that we want to focus on is a parallelogram, and that's a quadrilateral with 2 pairs of parallel sides, okay? So it looks something along the lines of this guy, okay? Now, it's called a parallelogram, hint, because we have opposite sides are parallel, okay? So my top side and my bottom side are parallel, and my left side and my right side are parallel, okay? So it has 2 pairs of parallel sides. Parallelogram, top side, bottom side parallel, left side, right side parallel, okay? Now, T43 says the sum of the measures of the angles of a quadrilateral is 360. Okay, so just kind of like the idea of the sum of the measures of a triangle add up to 180, the sum of the measures of a quadrilateral add up to be 360. For instance, if this is angle 1, angle 2, angle 3, and angle 4, okay, then the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 plus the measure of angle 4, all of those would add up to be 360 degrees, okay? So the sum of the measures of the angles of the quadrilateral add up to be 360 degrees, okay? T44, opposite sides of a parallelogram are congruent, okay? So for any parallelogram, remember that means we have parallel sides, top and bottom, left and right. Their opposite sides are also congruent. So this side is congruent to this side, and this side is congruent to this side, okay? So opposite sides of a parallelogram are congruent. The opposite sides are going to have the same length, okay? T45, opposite angles in a parallelogram are congruent. So again, we have our parallelogram. Man, gotta learn how to pronounce. Top side, bottom side are congruent. Left and right are congruent. But opposite angles are also going to be congruent. So this angle and this angle will be congruent, and this angle and this angle will be congruent, okay? So opposite angles in a parallelogram are congruent, okay? That's T45. Now, Theorem 46 here says the consecutive angles of a parallelogram are supplementary. Well, let's break that down. What does it mean to have consecutive angles? Well, consecutive angles is one after another in the order that they appear. For instance, if we're calling this, let's say 1, 2, 3, 4, okay, then in consecutive order, 1 and 2 would be consecutive angles, 2 and 3 would be consecutive angles, 3 and 4 would be consecutive angles, and then 4 and 1, okay, so one after the other. So with that in mind, if they're supplementary, remember that means they add to 180, then I could take a pair of consecutive angles like angle 1 and angle 2, and the measure of angle 1 plus the measure of angle 2, that would add to be 180 degrees, okay? That would add to be 180 degrees, okay? So anytime we have consecutive angles of our parallelogram, they're supplementary, they add up to be 180 degrees. Okay, which that would also be the same. We could do the other ones too. We could say the measure of angle 2 plus the measure of angle 3 adds to be 180, which makes sense because remember opposite angles have the same measure. So if angle 1 and angle 2 are supplementary, then since angle 1 and angle 3 have the same measure, angle 3 and angle 2 would also add up to be 180, and so on. Okay? So then that's T46. T47. The diagonals of a parallelogram bisect each other. Remember, when we bisect something, it's talking about cutting it in half. Okay? So the diagonals of my parallelogram, they're not very straight, but they bisect each other. Okay? So in other words, this guy and this guy have the same length. This guy and this guy have the same length. Okay? So the diagonals of my parallelogram bisect each other. They're cut in half. So my diagonal here, this guy over here, would be cut in half, so they would have the same, those segments would have the same length. And then same thing for this guy here. Okay? Now, a rectangle. Let's get into some other definitions here. So these guys are definitions. Okay? Definition, and this is also a definition. Okay? A rectangle is a parallelogram. So a rectangle is a parallelogram, but it's a specific one in which it has 4 right angles. Okay? So I still have parallel sides. Okay? These sides are still parallel, but a rectangle specifically, the angles are all right angles. Okay? So that's a rectangle, a parallelogram with 4 right angles. A rhombus is a parallelogram with 4 congruent sides. All the sides are the same. So it's a parallelogram where we have opposite sides that are parallel, but all the side lengths are the same. They're all congruent to each other. They all have the same length, all have the same measure. Okay? Now, a square. You might think, well, that almost sounds like a square, right? Well, not quite, because a rhombus doesn't have to have 90-degree angles. But a square, that guy right there is a parallelogram, or you can think a rhombus, because 4 equal sides. A parallelogram with 4 congruent sides and 4 right angles. So not only does it have 4 congruent sides like a rhombus, but it also has 4 right angles. So the sides are congruent, but also, whoops, can't zoom in, there we go. The angles are 90 degrees. Okay, so it has 4 congruent sides and 4 right angles.